In this lesson, we talk about double integrals of functions of two variables. In fact, the way that we do that, we talk about how to compute double integrals of functions of two variables. As you know, in calculus 1 and 2, we had in calc 1 and 2, when we had a definite integral, it was the integral from a to b. And by the way, a or b or both could be minus or plus infinity of f of x dx. So you were integrating over an interval. In today's lesson, we talk about functions of two variables. Instead of dx, we have dA, the area infinitesimal. I'll let you know what it is. And here, instead of intervals, we integrate over some rectangular region. Of course, we can have non-rectangular regions, other types of regions, but here our focus is a rectangular region. So this region R is like all x and y's, such that x is between two values, a and b, and y is between two values, c and d. As you might remember, in the case of calculus 1 and 2, if the function was a positive function, the integral measures the area under the graph of the function. What about in this two variable case? You know that the graph is a surface, and if the function f of x and y is a positive function, meaning that the values are positive, then that double integral measures us the volume under the surface. So that's the volume. From the top, it is bounded by the surface of the function. From the bottom, by the plane of xy. But here our focus will be on computing this double integral. And we assume that f of x and y is a continuous function. So here we are computing this double integral of f of x and y. And as I mentioned, R is a rectangular region. X is between a and b, and y is between c and d. And f of x and y is of course, a function of two variables. It's a continuous function. So in this situation, we have two options to set up the integral and calculate the integral. And based on these assumptions, it turns out these two will result in the same answer. One is first, so I have two integrals. First, I compute the integral with respect to x from a to b. Pay attention that x is from a to b. So now dx is done first. And after doing this, the other integral is from c to d with respect to dy. So in fact, this dA here, the infinitesimal area is dx times dy. So in this situation, I do this integral first, and then I proceed and do the other integral. I have the other option, and they result in the same value. And the other option is, first, I do the integral with respect to y, so f of x and y dy first, and y runs from c to d. And then after that, this will be inside another integral, and the other integral is the integral from a to c, I'm sorry, a to b, with respect to the variable x dx. At the end, these two will be the same value. They are equal. But we should be careful that how we set up our double integrals. If the inside one is with respect to x, the inside integral should have the limits which are for x from a to b. And if I start with the inside integral with respect to y, then inside integral should have the limits of c and d. For example, I want to do the integral over some region R, some rectangular region R, and the function that we have here is 6x squared y. So I want to calculate this. Now let me explain what R is. R is the region xy such that x is from 1 to 2, and y is from 0 to 3. This rectangular region. Over this rectangular region, I want to find the integral. As I mentioned, in the case of if the function is positive over that rectangular region, we get the volume. But in general, the value could be, if the function is not necessarily everywhere positive, it doesn't give us the volume, and the result could be positive. The result of the double integral could be positive, negative, or 0. This question from the beginning could have been given by using the limits of these two integrals. So the question could have been given like this, the same question. The integral x runs from 1 to 2. If I go with x first, so dx would be for the inside integral. And y goes from 0 to 3. So dy goes for the exterior integral. And the function is 6x squared y. So for a moment, let's focus on the inside integral. For this inside integral, I should integrate with respect to x, meaning that I should deal with y as if y is a constant. So for this integral, y is a constant, and also 6 obviously is a constant number. From calculus 1 and 2, we know that a constant can come out of the integral. So this comes out of this 6 and y, excuse me. They come out of the inside integral, not outside integral, because the outside integral is with respect to y. So in the next step, I will have, so first let me write that outside integral, 0 to 3 dy. So 6y comes out of the inside integral. And I just need to find the integral of x squared dx, where x runs from 1 to 2. This is quite simple. As you know, antiderivative of x squared is x cubed over 3 using the fundamental theorem of calculus. Then evaluate at these two numbers, the limits of the integral. At 2 is 8 over 3, at 1 is 1/3. So this is going to be equal 8 over 3 minus 1 over 3, which is 7 over 3. So far I have the integral from 0 to 3, 6y times 7 over 3 dy. I can simplify this more. 6 over 3 is 2. 2 times 7, 14. 14 is a constant, can come out of the integral. So the integral from 0 to 3 y dy. This is like an integral at the level of calculus 1. So 14 times antiderivative of y is y squared over 2. And I should evaluate at the limits of that integral. So 14 times at 3 squared, 9 over 2. At 0, 0 squared over 2 is 0. And then 14 times 9 over 2 is 63. So the value of that double integral is 63. You could have also done the integral with respect to y first. So if you do that, you needed to set up the integral with respect to y for the inside integral, and with respect to x for the outside integral. So from integral from 1 to 2, and then from 0 to 3 of the same function, dy dx. So I ordered I changed the order of dy dx. So that's why the integral with respect to y is inside and the integral with respect to x is outside. So I need to do this first, and I should deal with x as a constant and do that. And then after doing this, I go to the next step and do with respect to x. You can try this on your own. And at the end, whatever order we chose, at the end we should get the same answer, 63. So you can try this on your own to make sure that that's a good practice, that you should get the same answer as the other order. So in some examples, the question will be like this, and the region is given, or sometimes from the beginning, it tells us what the integral is from where to where. Let me do another example. As usual, before watching my solution, try to do the example on your own. The integral from 0 to 2 and the integral from -1 to 0 of 2x plus 4y dx dy. Obviously, in this order, the inside integral with respect to x. So the region we are integrating, x runs from -1 to 0 and y runs from 0 to 2. So you can pause the video and try this on your own, and then check your answer with my answer. So in this order, I should do the inside integral first. So keep the outside integral like this and focus on the inside integral. For the inside integral, it's with respect to x, so I should deal with that as I should deal with y as a constant. The derivative, the antiderivative of 2x, of course, is x squared. Antiderivative of 4y, as I said, with respect to x, 4y is a constant. Antiderivative is 4yx. And I need to evaluate at the endpoints -1, 0. So for now, I don't apply the exterior integral. So as we know from the fundamental theorem of calculus, evaluation of this at 0 minus evaluation of this at -1. At 0, obviously, when x is 0, 0 plus 4y is 0 is 0, so 0. At -1, x is -1, -1 squared is 1, and 4y times -1 is -4y. So let's see what we have so far. The integral from 0 to 2. Here, what I have is just -1 plus 4y. So -1 plus 4y dy. Now, this is like a simple calculus one. Antiderivatives and antiderivative with respect to y is antiderivative of -1 with respect to y is -y. And antiderivative of 4y is 2y squared. Now I need to evaluate at these limit points, meaning that this at 2, which is -2 plus 2 times 2 squared, which is 8, minus this function at 0, which is just 0. So the answer is 6. Again, for this integral, if you change the order of integration, at the end, you should get the very same answer, meaning that for the same function, if you integrate with respect to y first, so if dy comes first, then the limits of the inside integral will be from 0 to 2, and dx outside, so the outer integral will be from -1 to 0. At the end, you should get the very same answer.